Assumptions, because we're going to get to Mancova, which has every assumption we've ever covered.
Wow.
And more. And you should have a little cheat sheet of assumptions to make sure. Okay, so number 6 is hostility was the variable that was had to be significant and important. I think most people got that. And the model correctly predicted. I think everybody got that one. Number 7, 61 people. Some people missed this one. A 1 unit increase in family history increases the odds of getting CAD by 63%. Some people said 49%. Why? Number 8. But most people got that. This was the one that was supposed to be the other way of doing the wall statistic. One variable is not significant based on the Wald chi-square statistic. Another way to assess this variable would be use the log difference scores with that variable isolated instead of the Wald statistic. It's the only answer that's even close of those 4. Some people missed it though. 10. So a lot of people missed this one. I guess we're just taking this. But the advantage of a logistic over a chi-square is you can control for more than one covariate. So
I just don't remember us talking about more than one covariate, really.
well, covariates are the predictors, really, right? So in logistic, but the best test takers, a lot of you missed this one. So let's give everybody 2 more points for that one.
Wait, so when I think of covariate, I just automatically think of ANCOVA.
Remember, look at the logistic. No, you can't see it. In logistic dialog box, the predictors are called covariates. So that's probably why that got confusing. So if I had said you can control for one or more than one predictor, it would have made it an easier question. So some people got it right, right? Who got it right? Yeah, so you can give yourself an extra 2 then. So everybody gets 2 extra points for that one. Gonna raise these scores up a little bit. Sensitivity, everybody got 12. Some people didn't get this one. This was the giveaway question. Luckily, nobody put Smith and Wesson. Hosmer and Lemshaw was the only name associated with logistic. That was supposed to be a total giveaway, and I think 2 or 3 people. She was even on the slide. This one was a little trickier, but you needed to get it. So if you looked at the relationship between CAD and stress on the first page, right? You saw that the relationship was 0.21, and you had to square it to get 4% in common. So that was a little tricky. Then you had to look to see that CAD is a dichotomous variable, stress is a continuous variable. What kind of correlation is there between a dichotomous and a continuous? 8 points by serial for the next one.
Wait, can you say where the 0.21?
See on the very first page of their actual test?
Yes.
The 0.21 correlation? You've got to square that to get the percentage of variance in common, right? Okay, CAD is a dichotomous variable, right? You either have it or you don't. Stress is a continuous variable. It's on a continuous scale. So the relationship between a continuous and a dichotomous is a point by serial. That's the kind of correlation.
The 0.56 is post versus hostility. That's right?
Yeah, that was hostility. That wasn't the way we were looking at it. I was asking between the correlation between, between hostility. Yeah, so hostility is a continuous measure, sorry. Hostility is a continuous measure. CAD is a dichotomous measure, so it's a point by serial. Would have been any of those actually would be point by serial with CAD. So you have to kind of remember that. That's sort of a decision tree question. Good specificity would mean we did get, everybody got that one. Narrow C curve, most people got it. The only thing close to a cutoff was 7.5.
Yeah, Yeah, she showed me that, yeah, I didn't even see that on the.
Look at the ROC data. The second page of the ROC data. Page 3 of it. So it sort of shows you the numbers and the specificity and the sensitivity and the false alarm rate. So the only one, I mean, 1.5 would be way overbalanced in terms of too many false alarms. And 15 would be way overbalanced in neither of them. That's terrible. And 0 doesn't work at all. So 0 is nothing. So the only one that could be would be 7.5. Most of you got that. I think everybody got 17. Now we had some problem with the ANCOVA output. So ANCOVA can be used for all of those D. Most people got that. And ANCOVA is sensitive to homogeneity regression. Most people got that. A few people missed it. So that's the big assumption for ANCOVA, homogeneity and regression. 20.
Quick question. I remember you were talking about ANCOVA and outliers being a big issue. Or am I confusing it with like discriminant function or something?
Yeah,
I remember you talked about
discriminant normality is important for discriminant.
Okay.
ANCOVA is pretty robust against violation of So in the output, the 4.961 tells you that the main effect is significant. That was the actual NOVA. The 9.805 means the slope of the regression lines are not 0. That's the test of the regression. That seemed like it would be easy, but some people.
What was the answer?
B.
You got it right wrong, you got it right.
Oh, sorry. Good.
B.
2021 B.
Oh, since it's a covariate, it's testing.
If it's covariate significant, so that means that there is not a 0 slope between the covariate, or there's a correlation. It's the same thing. So put that on there. If I marked it wrong, let's see. Put that at 22. Remember, this tells us that homogeneity regression is not violated R. And you had to look to the later output to see that the interaction between the CV and the IV. What is that? Page 3, right? No, not page 3.
Page 3 of the
ANCOVA one.
Or the front physical page 3.
Yeah, they're all different.
Third stable page.
So if you had to look at the interaction IV times CV, that's where you get that number from. And the 0.419 is the significance level. The F is 0.914. That means that there was no violation of homogeneity regression. ANCOVA is used to report post differences in a pre-post design. The data that's being used are adjusted estimated means. We talked about, remember, the estimated ones, which are called, the adjusted ones that are called estimated in SPSS. I actually wrote it on there so we were confused, but didn't help everybody. Violation of equality of homogeneity regression means that, I think everybody got that, the relationship to the covariate dependent variable differs across the treatment groups. Some people missed this one. The means 7, 11, and 12 were the unadjusted means, and the other ones were the adjusted means. We just looked at one. This has been a real giveaway, but not everybody got it. The relationship between CV and DB is assumed to be linear. Assumption of ANCOVA need to be especially observed in quasi-experimental or static group designs.
So I transcribed the TA session, and
what I had down for number 27 was that you don't want to use ANCOVA for quasi or static designs, so I interpreted that question as,
What would you say instead for answer?
I put non-parametric, but quasi-experimental or static designs, just to clarify.
Well, but the assumption of ANCOVA the assumptions need to be especially observed. So your thinking is right, you just didn't put the right answer down.
So if they're not,
So if
If
they're
you
not
don't
met,
want to
you
use
would
it-
definitely don't want to use a quasi-experimental or static curve design.
okay, I couldn't understand the question. All right.
Again, you put one down that you didn't know anything about, then don't ever do that. If one of the answers is something you don't recognize, don't choose that, even if you don't think the other ones are right. That's almost never right.
Okay.
28 is treatment by blocks design, we mentioned. I forgot that. 29, order of ANCOVA to increase power, the CV and the DV must be correlated. I said that like 3 times. Based on the data, now here, I couldn't get this one. Homogeneity of variance is not violated. Look at the data. The Levine's test is not significant, right? People getting confused about what's supposed to be significant and what's not.
Yeah.
This is first semester. Remember, homogeneity of variance is not supposed to be violated. Not supposed to be significant. The Levine is significant, that means you violated the assumption. So that was a silly mistake some people made.
Yep.
The main effect for group is significant, and then how do I know it's a large effect? For the next one.
Why is it large?
Why is it large? Somebody tell me, why is it large?
Because the effect size.
Yes, which the effect size, the partial eta is 0.332. Remember, anything above 0.15 is considered a large effect. Well, it's above 0.3. If you go by 0.3, it's above 0.3.
0.4 was small.
No, not for an eta squares. Remember, for eta squares, it was 0.15 or above is large, 0.08 to 0.15 is medium, below 0.08 is small.
Because 0.332 means about 33%.
33% of variance is accounted for by the main
It's
effect.
really big.
That's big, I'd say
Yeah,
that's
it's
big.
huge.
I couldn't really remember the
Nearly 5 factor, that's 50%. Countable.
Is that coming?
You say those cutoffs.
Yeah.
These are from first semester cutoffs, so like 0.15 or above would be considered a large effect for eta squared. 0.15 or above, 0.08 to 0.15 is medium, below 0.08 is small. Now, it depends on what effect size you're using, right? So for D's, there are different effect sizes. We'll talk about that in a minute. Number that tells us the amount of variance accounted for in the discriminant function was, most people got this for 2C. Just needed to look at the canonical correlations. That one was pretty good. Some people missed this one. Remember, the boxes M is close to significant might indicate a violation of all of those. Homogeneity of variance would make it go big. Normality, violation, normality, homogeneity, covariance. Any of those would make the boxes M get larger. We'll do that question again on MANOVA, so remember it.
Which one? The box.
Number 33, boxes M. It's also an assumption. It's used on MANOVA the same way. Standardized canonical DFA coefficients are analogous to beta weights. Just have to remember which ones are which. Structure coefficients are correlations between the variable and discriminant function. 93.3% of the cases were classified correctly. Variable most successful was aggressiveness. Discriminant functions are found in the data set. There's only one. It shows in a bunch of places. Some people thought more.
It's aggressiveness because it's at the top.
Well, I think maybe they got ranked.
Even though diastolic is 0.9 and aggressiveness.
No, you had to look at the standardized weights to decide that.
Where?
Discriminant.
You can't call it a discriminant function.
You need to look at the,
Standardized but non-equal discriminant function.
yeah. Exactly. Those are like beta weights. So we're going to go over those again in number 2. And this one was a little harder. Now, most of you figured out how to plug in the formula for this equation. So you put in the formula, and some of you didn't do the math right, so it should have come out with a plus 0.7.
I said something else there.
I know. So
High five for putting it on with last second.
So if you did the math right, it came out with a plus 0.7, right? If you plug those numbers in, so you look at the equation from the original discriminant equation, which is 0.238. We got to find it here. Times 10 plus 120 times 0.026 plus 200 times 0.008 minus 6.4. The constant.
Yeah, so you got
Yeah, 6.8. Yeah. So then if you do that math, you come out with a plus 0.7, right? Yeah. 0.7, something close to that. 0.7 something.
But you're there plus so Dr. Burns, I should get half a point.
I thought about it, but I figured this is grad school. You can't translate that into that.
You have to remember the gauntlet that you ran to get to grad school.
All right, now why did so many people miss 40?
Because subject 23 did not show up at me.
Oh, it was supposed to be.
I know.
Oh.
I found that out in the hallway. I was like, no!
I thought it was no subject.
So give yourself an extra point for that one, an extra 2 points for that one. I should have just said the subject didn't number 39. I didn't. Some people asked me, some people didn't. So it should have been a positive 0.7 gives you CAD, right?
Yeah.
Did you explain how to figure that out?
Yeah.
Well, because look at the discriminant, the cutoffs, right? Any negative number was going to be
Where do you see the
the last thing in discriminant.
Oh, the classification.
Yeah, so anything negative would be no, anything positive would be yes, basically, with sort of a zero middle point. The problem is 23, because it was from another test, I forgot to say the subject in question number
So
39.
since we got 0.7 because it's,
Yeah, so it would be a positive number, right? So that person would be classified as having CAD.
Okay, explain me why it's a positive and negative again.
Well, you see the two functions, the average for the people with the negative was minus 0.120, average was positive. So anything on the positive side is going to be closer to yes.
I think I did the right thing, but I just picked the wrong one. So, but what I did was, I knew that those centroids are like an average of the discriminant scores for that category.
Yeah.
Right? And I just saw distance from that person from 39, the distance from that, their score to the mean, and which one was smaller. Like, does it more have to do with the distance between, or?
No, it has to be above, the cutoff was 0, and so it just was above the cutoff.
Oh, it's just
Above
zero.
the cutoff, but the cutoff should be, I don't know if it says it in this output, but it's specified somewhere.
So basically, we know it's positive or negative.
So you can give yourself 2. If you got it right, you get the bonus. If you didn't, then you get 2 more points for that.
Number 40 plus 4 plus 2.
Plus 2. Every question's 2 points.
So if you got it right away.
So everybody gets basically extra 4 points. You get an extra 6 points. That'll bring the distribution backward.
What is it? How much is the denominator?
In which? Oh, yeah. Yeah, what I did is I took 2 points off for each question instead of 2.5 points off for each question. So we're going to not give you back 2.5, we're going to give you back 2. All right, so pass the test back to the TAs and give me the other sheets. So we're moving into our final stuff here. Next week, Dr. Dellenberg's class is going to be in here, so we're going to get here early for the seat. She's got to go to a conference. So today we're going to just cover a short lesson on meta-analysis.
Can I ask a question about the project?
Yes. So we want to at least get you started. The project calls for doing all the different things for the semester. So we have a big data set to do all the things we've done. Regression, notice. So as soon as we just begin to cover the NOVA, we'll give you the data set that you can start working on right now. Regression, but not a write-up, and a couple short answers. And then about some regression plus mediation, moderation, those kinds of things. And then then you do it in ANCOVA, and answer a couple questions about ANCOVA. You do logistic, and answer a few about logistic. Multiple regression is the one that you have to write up, like a full write-up. But the book has write-ups on all these things, so you can kind of look at them as models for how to write them. MANOVA, MANCOVA.
The final's cumulative or?
The final's cumulative, yeah. So for the final, we have cumulative, bunch more data outputs, kind of from the whole semester, and then just as fewer questions about each one, and then there's a decision tree final, just exactly like last semester. And then the project, the big part of it is regression. That's the most points of regression, but then there's points on logistic, ANCOVA, discriminant. I don't think we have our C curves on there. I don't think so. I can't remember. What am I forgetting? MANOVA. I said MANOVA, MANCOVA. I think that's it.
Is the project due the day of the final or the week after?
We have it on the syllabus. I think it's the week before. Is it? I can't remember when we tried to work it out. It's not written on there? Was it?
The project given out.
Oh. Yeah, so we're giving it out early enough, which is next week, right? So we'll give it out next week. If we did 2 weeks from that, that's not the day of the final, is it? It is the day of the final.
Yeah.
So our final comes the week before that extra week. So if we want to, I don't know, last semester we did that, we gave you that extra week to do the project, but I'm not sure if people like that or not. It means when you're done with your finals, you're not really done.
I'm okay with that. Yeah. So if you want to.
So do we have the option of turning it on?
Yeah, sure, you can always turn it in earlier. Yeah, so I guess we'll just make it do the next week. We don't need it the grades aren't due for a while, so we can grade them afterwards. You won't have it graded. I'd recommend doing it before the final anyway, because I think it's a real good preparation for the final, or at least to do the analyses and look at them. So. But I think for some people, if you're time pressed, you have other finals, you can hand it in next week. Okay. Yeah, the week after the final. We have that extra week because we didn't miss any classes. So, they put an extra week in the semester for people who missed classes. We didn't have any missed. So. So a quick going over topic, meta-analysis. Meta-analysis is more and more common. Any of you working with Dr. Ellis soon, he may try to convince you to do one of these for a dissertation. Kind of looks like an easy way out, but it actually is a lot of work, maybe more work than an outcome study or something. Meta-analysis is a term coined by Gene Glass in the late 70s, as president of a statistical group. It was the thinking of a lot of people that traditional lit reviews, which we basically had at that time, mainly in journals like Psych Bulletin or Psych Review, two very prestigious journals in psychology, plus another thing called Annual Review in Psychology, where they do annual reviews of developmental, social, perception, all the big topics in psychology, that even though those were very useful, that they still were completely dependent on somebody's opinion of reviewing the literature. So the idea would be maybe there's a more quantified way of looking at the literature that would allow us to combine results. The results quickly caught on also in medicine and in pharmacology especially. A traditional review based on reviewers' analysis of its study themes, which are still very valuable. Meta-analysis collects the essential empirical results from multiple studies and draws conclusions about the overall effect across studies, no matter what the original study conclusions were. Thus, meta-analysis becomes a research study on research studies, hence the term meta-analysis. Developed substantially both in methods and in applications. And you'll see these names, Larry Hedges, Inga Molken, Hunter Schmidt, these names come up again and again when we talk about it. The literature review to do the meta-analysis should be as systematic as primary research, and the study characteristics and design should provide a context for interpreting the study results and conclusions. So one of the things that's possible is that you get a biased sample of studies. So the person doing this has to be exhaustive in making sure you find all the studies that there are in a given area when you're kind of reviewing these. And you should be very clear about what your criteria are for inclusion and exclusion for those studies. Sometimes some meta-analysis people, you can bias the results by being extremely strict and only letting some studies in. And especially if those studies all happen to be the positive ones or the negative ones, then you can get a bias in how it works out. So you have to be aware of that, and you'll see the news. So you first collect studies on a particular topic, information about studies that are collated and coded. Results of each study are translated into a common metric, which we're going to talk about, the effect size metric. Analysis is then conducted to summarize the effect size across studies to analyze relationships between covariates and effect size. When you do so we now change our focus from a number of important issues in science, including publication biases. Somebody did a study once on attribution theory and found 95 non-significant studies for the 5 published studies on some aspect of attribution theory. So if you go and look at dissertations, there's a million of them. We've got a really good example of that right here. We had a faculty member who was a disciple of Jamie Pennybaker's studies on writing, emotional expression writing for therapeutic intervention. It's a popular topic because it's pretty easy to do. You find a population, you can write for 3 days about whatever it is. Another population writes about the weather or something, and then you do some outcomes at the end of that. Well, we probably had about 14 dissertations on that topic. 2 of them found nice significant outcome results. They're in different areas, and the other 12, the 2 that did find them got published. The 14 other ones, the 12 other ones that didn't find anything at all from writing, no effective writing, were just in the library still today. No one's ever looked at them. So there's a publication bias that only things that are significant get published. It's an area where there's a lot of interest, especially a lot of dissertations. Sometimes what you have to do the meta-analysis is go look at Dissertations International and scour through a lot of really lousy dissertations, but also some good ones to try and find what's really out there in terms of that. And that could lead to a significant publication on this. And we're going to talk about things we talked about a lot already. So the effect size of meta-analysis is really sort of the new dependent variable. We don't really look at significance anymore. That's going to be included in the inclusion or exclusion. And what we really want to look at is the effect size. We want it to be some standardized way so that all studies are in the same metric. They can be directly compared. And we can use a number of different indices of effect size, which we should remember now. I think we've got them all covered. We could use standardized mean difference, which is the Cohen's d. How many standard deviations is one group away from the other group? So for instance, if we're doing SSRIs, it would be the difference between the placebo and the actual SSRI that was being used. We could use and those are expressed in standard deviation units. Those are the Cohen's d's. You can use a correlation coefficient to affect it, just like an eta squared, or like an eta. So some people use just an R as an effect size measure. And we've just covered odds ratios. So odds ratios can be a way of doing it. To do odds ratios, you have to use the outcomes into dichotomy. You have to dichotomize the outcomes. So what you'll see in some of the ones I'll present to you, some people will say, look at the Cohen's d, or a version of the Cohen's d. The Hedges G is the modern version of the Cohen's g. I think that's coming up in there.
That's Larry Hedges, the same.
Larry Hedges is the guy, yeah. So he's got it's just a slight modification of the d that takes into account sample size and affects some other things. So most everybody uses one of those modified ones. So it's just the same as the idea is the same as the Cohen's d. So let's say you're looking at what we're going to look at. One of them is CBT for anxiety disorders versus some sort of placebo or comparison group. So Stefan Hoffman, a colleague of ours at Boston University, did a meta-analysis of that comparison. You guys in health have seen this one already. And what he looked at was these Hedges G's for the differences between the two in terms of standard deviation units. But he also said, well, let's divide people into, do they meet the criteria, say, for OCD or not at the end of treatment, right? Or some cutoff could be put on, like are they above or below a Beck of 16? So you can do that as well. Then you can use odds ratios to look at the effect sizes as well, because odds ratios would be like we just studied in logistic, of 2-to-1 chance or 3-to-1 chance, odds 3-to-1, 2-to-1, 1.2-to-1, whatever they might be. So a lot of people use odds ratios, or if the outcome is simply dichotomous, survival, no survival, relapse, no relapse, got out in time, didn't get out in time, passed the comp, didn't pass the comp, then you would just use odds ratios. You can't really use Cohen's d's in those, they have to be odds ratios. Kind of and they should be, the numbers should be independent of sample size. And we'll look at sample size as a bias. So you need to find all studies. This is where the work comes in. And you start off with a PubMed search and a Cyclid search, and you think you got everything that's out there, and then you follow all the references in every article you found, and you find 14 more articles that were not in PubMed or were not in Cyclid that were in the references of the articles you found, and you go to the articles, references in those articles, and see if there's anything in there that's relevant, and on into infinity. You look at unpublished studies any way you can. I get probably every 2 or 3 weeks I get a request from somebody doing a meta-analysis that some study we presented at a conference but never published. I want to know if they can get all the results of that study, which is a real pain in the butt for me. I got to go find the exact results of that dissertation somewhere and send them off to England. There's a place called Cochrane Reviews in England that do the very good reviews in certain areas, and they're very prestigious reviews. So I get, every once in a while, I get a Cochrane request for something we did, presented as a poster, but didn't get around to publishing. So that means somebody's really thoroughly searching, finding every reference there could be to something.
And how discriminate do you have to be with that? Just say if you're doing a meta-analysis of like alcohol or something, you would have to
Well, you would do
broad or discriminate.
discriminate. Yeah, well, you'd have to decide when you're doing, like, probably no one would do a meta-analysis on some alcoholic forever, but they might do one in the last 10 years.
Okay.
So you'd say meta-analysis since 2000 to the present, meta-analysis of the effect of smart recovery on relapse or something. And then there will still be hundreds of studies, but not thousands probably. I don't think anybody does anything much more than, 50 to 100 studies is a lot.
Okay.
So then you have to be careful about not comparing apples and oranges, making sure that they're the same basic thing. That's not so easy in a lot of areas. Like some people, I can do a meta-analysis on yoga. Well, what are we going to include? What are we going to exclude? Does Ashtanga count as Hatha yoga? These are so different. Is it Bikram? Is it yoga in a hot room or not? Is it, if it's Hatha yoga, how experienced, do they use the exact same poses, the exact same techniques? No two instructors do Hatha yoga the same way. We've never seen, we've not observed. There's nothing even close to some of them and the others. Some of them are great, some of them are terrible. Ashtanga is better because it's a series of actual prescribed poses in a certain order. So the study we did was on Ashtanga. That was a little bit easier to standardize. But it's really a mess if it's the area that doesn't have standardization. How about CBT? You're going to do CBT studies? Are you going to look at CBT, a CBT, a CBT? Well, not exactly. Some people do ACT and they call it CBT. Some people do psychodynamic therapy and call it CBT because you get paid for it. So now you got to really be careful what criteria were they actually using. It's very tricky sometimes. And you want insurance. So these are what I said. We can use bibliographic stuff, authors, and you write to authors in the area. Have you heard of anything more in this area? And they don't respond, so then you have to bug them. And, review articles, reference lists, hand searching, journals, government reports. So the strengths are poses the discipline of the process of summing up research finding, represents findings in a more differentiated and sophisticated manner, capable of finding relationships across studies that are obscured by other approaches, protects against over-interpreting differences across studies, can handle a large number of studies that would overwhelm a traditional review. Weaknesses, requires a lot of work. Mechanical aspects don't lend themselves to capturing more qualitative distinctions between studies, as I was saying a minute ago. Comparability of studies is often an eye of the beholder, like CBT versus something else. Include blemish studies. Sometimes people aren't careful about only putting in very high quality studies. Selection bias because it's a continual retreat. Like you said, they could do anything. And analysis is really kind of a correlation analysis. So the standardized mean differences, what we said, group contrast, research treatment, naturally occurring groups, odds ratio of dichotomous outcomes, or for treatment groups, and correlation with associations. If all the variables are correlational studies, you just use an average correlation. Those are the formulas for the effect size, but you can also use a pooled effect size, where you actually put the size of the studies in with a little different estimate of what the S in the bottom is going to be. So this is just would be mean 1 minus mean 2 for the two studies you're comparing, like placebo versus active ingredient, and then you use a pooled variance for the denominator to try to get an effect size, which is what we usually do anyway. Commonly called columns D, and sometimes the edges G as a modification. From relation is just the R. And we just did odds ratios, so we know what those are. You can convert p-values, t's, and f's into standardized effect size metric being used in meta-analysis. You can just derive the effect size from the t. A little formula for a t-test, for instance, is if all they report in the study is the t, you can do t squared minus 1, t squared plus n1 plus n2 plus 1 equals an omega squared. And you can also turn that into a D or edges G. Sometimes you have to kind of work to get what you need out of that. And actually there's for the D's, those are the rules of thumb. 0.2 would be a small d, 0.5 is a medium, 0.8 would be 0.8 or above a large. That's kind of a conservative view, or a liberal view, I'd say. Correlation coefficients above 0.4 are considered large, but remember 0.4 is only 16%. So.
Can you explain how that makes sense here?
Well, sometimes all you've got from a study is a t-test between two things.
Okay.
You want to turn it into an effect size, there are formulas to turn those f's and t's into effect sizes.
Okay.
So then you can do that if you need to do a meta-analysis. That's just one example of those. And of course, those rules of thumb aren't very iffy. But they're kind of fitted with most analysis. I said this already. So let's look at one. It's a very important one for us. It's a little hard to see on your graph, I think, but I can make a bigger copy if you actually want it, or you can go online and get this yourself if you want it. On this one, what Stefan did was he found studies, many studies as he could, that met high quality criteria for anxiety, I always forget what ASD means, anxiety. It's like a mild anxiety attack, but I forgot what the letters stand for. I know the guy Brian too, so that's true. I'll think of it. Anyway, for basically anxiety attacks, for generalized anxiety disorder, for OCD, for panic disorder, for PTSD, and for seasonal affect. No, not seasonal affect. For it's not seasonal affect. It's stress. There's an DSM: stress, anxiety, stress. Is it? Acute stress. That's the first one. Acute stress disorder is ASD. And ASAD is not, it usually stands for seasonal affect, but it isn't here. It's another one was mild, wasn't it? Social anxiety.
Nice.
Woo! Easy. Much better. Okay, so then the Hedges G's are your D's, right? Those are like the standard deviation of differences. All these studies have comparison groups or placebos. That's why there's so few of them in each category. There's many, many more studies without good placebos, just against treatment as usual or against nothing. But it's hard to find them where they actually did placebos. So if you look, you can see for acute anxiety, ASD, the G's were 1.49, 1.28, 1.66, and 1.08, although they all come out of Brian's lab in Sydney, Australia. So that's a reason for suspicion. You want to see him out of other labs as well. He's a guy that studies that. But those are good effect sizes, right? So that means that the group, a placebo group, was over about 1.5 standard deviations worse than the group that got the treatment, CBT. These are all CBT. So for CBT, it looks like that's pretty effective. He gets the lower limit, the upper limit, the Z value, so you can see Z's above 1.96 would be significant then, meaning that you can do a Z translation of that effect size of how likely is that due by chance alone? How different is it from just a zero effect size? If you look at the GADs, there's only two of them. They're both 0.57 to 0.44. Those are pretty poor. Right. OCD generally, and the FOA had a 1.65. Another student of hers a 2.08. That's a very good effect size. One other group got only a 0.74, so it makes you wonder about that. So those are pretty good. OCD is one of our better treatment outcomes. The CBT works well for OCD. Now the ones that aren't so good, panic disorder, they're all down around the 2s, 3s, and then one reach the 4. So when you hear people say that CBT is a very effective treatment for panic disorder, it does work better. These are all studies that found significant improvement in the CBT group versus the control group, but not much better. Right? They're only a third of a standard deviation better. That means a lot of people getting CBT are not getting better with panic, and some people are getting a lot better. So it's one of the things we do. We think that there should be some additional components to the CBT to make panic treatment much more effective. In our clinic, we're much more effective with panic than that when using respiratory components. PTSD, unfortunately, is pretty poor too. Brian had one study of 1.48, but the rest of them are down in the mid ranges, 0.4, 0.3, 0.6. So clearly we're doing better than nothing with PTSD, CBT, but we need better treatments than that. We should not be resting on our laurels on PTSD or social anxiety for that. Those are not great either. So it kind of gives you a good picture of where we are with things like that. Over there, he just charted them with 0 being no improvement of the treatment group versus the other group. You can kind of see the better ones are over here. We'd like to get effect sizes really between 2 and 4, but we don't have that for very many things. I think now there'll be another meta-analysis pretty soon for OCD that's going to have some better effect sizes. OCD treatment's improved. People are a little bit better at the constraint and exposure of it. Plus you can do a lot better with cell phones now and with other modern technology and OCD and some improvement. You get the idea of how it works. I think it's a very valuable thing to look at. Here he turned them into odds ratios where he did a cutoff based on something that's shown there. No PTSD diagnosis, some cutoff that he used for whether they had it or not at the end of treatment. And then the odds ratios, we have a 56 odds ratio for the one study. For people who did not have PTSD but had acute stress disorder, that's an incredible one. And here you got a 53.95, so that means people who got the treatment were 53 to 1 times more likely to not meet the criteria for OCD at the end of treatment compared to placebo. Well, that's good. That's really good. That's what we would like to see a lot more of. But a lot of these are much lower odds ratios. So that's how odds ratios are used, and that's actually a good way to look at things as well. This is also looking at the effect sizes for the same studies that used depression as well. And not surprisingly, CBT doesn't work as well for something as depression. Here's one that I actually printed out on the back page for you, the whole thing, that probably is important for us, even though it's pharmacology, which is a pretty recent study, 2008, of SSRIs, looking at initial severity and the benefits of antidepressive medication. In this case, they did a little differently. They had the effect size for the drug pre to post and the effect size for the placebo pre to post. which is not the way we usually do it. We usually do a direct comparison between the two on different scores or something. But this is another way to do it. So the thing to note is that the placebos do darn well. This is not a happy finding for the pharmaceutical industry. So you kind of look down there, you can see a lot of positive D scores, not very many negative ones for the placebo. And you can get the change scores, which you want to see. And some of those Ds are pretty decent, but a lot of them are not so decent. So if you do a comparison with the placebo, you get very, very low effect sizes for SSRIs from mild and moderate depression. And now there's another study out that looked at data that was previously undisclosed by the FDA because it was unpublished. And if you look at mild and moderate, some authors have concluded that SSRIs are no better than placebo for mild and moderate, only for severe. So it's kind of good news for us, I guess, unless you want prescribing privileges, because it means that psychologists should be treating, we have better effect sizes for psychological stuff than we do for SSRIs. And even though SSRIs, so what happens in this case is the bias is within psychiatrists who don't do placebos. They give people the SSRI and they do a very careful decision on which SSRIs to give them. And they switch them every 3 months if that doesn't work. And something finally works, maybe the placebo effect, maybe something else. And they say, in my hands, I find great success with Zoloft or Paxil or whatever it is. But they don't know what they would have done if they had just given them a series of placebos to find one that finally worked. And if you do nocebos that have side effects, placebos that have side effects, you get even stronger equivalence between SSRIs and placebos. So you can see how important these meta-analyses are, because a lot of these studies by themselves concluded very positive results for SSRIs. Certainly good enough to get the FDA to approve them in the case of Bill. So you can see the usefulness of that. The one other quick thing real quick is, one more little handout here. There's another little more sophisticated way of looking at it, which is you kind of look at the sample bias on this pyramid plot, or funnel plots. You can see this more and more. I'll just mention it now and we can review it later. But what you do with these is you kind of, the next page kind of gives you a little key to what you do. On the vertical axis, usually you use something like the standard error of the study, because the standard errors are somewhat dependent on sample size, right? Standard error is going to be the standard deviation divided by the square root of n. So big sample sizes will have lower standard errors, right? So you can kind of look at what's the standard error and what was the standardized mean difference. And what you want is there not to be any bias by sample size. Right, so you'd like those funnel plots to be nice and evenly distributed, so that but if it turns out that the standard mean differences are 0 for all the studies that have really low standard errors, or is it high standard errors, whichever, then that's kind of represents a bias in the sample. In this case, this particular one was something to do with teacher expectancy effects, where they had. Turns out some of the studies had high teacher contact, other ones had low teacher contact. And the triangles are one and the other. So you can see that it was a bias depending on the contact. So it's a little more sophisticated way of looking at that. And then I showed you the odds ratio graph already. This was one on some medical thing, mortality. Unfortunately, these are all, they did all the odds ratios in the wrong direction, below 1. And so I would go back through and change those all to the other side of them so you can But you still see the idea that a bunch of studies, I forgot what the treatment was there, some treatment. Okay, we can go over that again later, but we're not going to spend much time on meta-analysis. We're going to launch into MANOVA next time, and then MANCOVA. And for MANOVA, we have to review everything we did in the first semester, because it's MANOVA times X. And then MANCOVA is all the assumptions of ANCOVA, MANOVA, ANOVA, regression, not logistic. So it's the mother of all assumptions. Okay, we'll start that next time.